So on the left side here, you can see that in the first part of the book, we had a lot of quantities which we called linear quantities. So we talked about delta x, which was the linear displacement, and we talked about v, the linear velocity, and a, the linear acceleration. And you can see the units that we used, meters, meters over second, and meters over second squares. And now we've been talking about angular quantities. So when we talk about angular quantities, we have theta, which is the angular displacement, and omega, which is the angular velocity. And we have this letter here, which is alpha, which is called the angular acceleration. And we see the units radians, radians per second squared. So they're kind of, you can see that they're connected a little bit. And there is a relationship between them. So for instance, if you were driving your car down the road, your tire would go through a certain angle, and the linear distance that your car goes would be related to the angle your tire moves through by the radius. So if you took the radius times the angular displacement, you'd get a linear displacement. If you imagine something at like a Home Depot or a Lowe's, there is a big spool of rope or wire. Think of a little kid who grabs hold of the end of that and then runs along the aisle. The kid might move, 20 feet down the aisle, but that spool will actually turn through a certain angle, a certain angular displacement based on the radius. And also, think about the little kid who's grabbed that little chain or wire or rope or whatever on a big spool. If the kid is running down the aisle with a certain linear velocity, well, it's related to the angular velocity depending on what the radius is. So if you know what the radius is and you know the angular velocity, then you would know what the linear velocity is. Same way, when your car is moving along the road, how does your car know what the speedometer should be saying? What is the linear velocity? All it really knows is what is the angular velocity of your tires. And if you know what the angular velocity of your tires and the radius, well, you can just put it through a little type of a few different gears, and then it can figure out how many miles you're moving through, and your speedometer can then tell you what is the linear speed. And the same thing if you're accelerating. If the little kid is at Lowe's and they're at rest and they grab hold of a piece of rope on a big spindle of wire, big spindle or something like that, they grab hold of it and they're not moving, all of a sudden the little kid turns and starts running this way, run, and they go faster. The spool of wire will be unspooling, and there'll be just as the kid has a linear acceleration, that spool of wire would have an angular acceleration as more and more wire comes off. So this is the relationship. So we have linear quantities, we have angular quantities, and then we have a relationship between the linear and the angular quantities. There is a relationship between the linear quantities and the angular quantities. But when we see a word problem in this particular chapter, it will mostly just be dealing with the angular quantities. So you're going to see a problem here when they talk about a washing machine starting its spin cycle. They might tell you the beginning angular speed. They might tell you the final angular speed. They might tell you how many seconds this thing has been moving to go from the beginning angular to the final angular speed. And they might say how many rotations, how many revolutions has that drum gone through. So it's going to be similar. In the chapter 2 of this book, we looked at things moving down the road, cars. So they gave you the beginning speed, the final speed. They might have told you the time it's taking, and they might have said, what's the displacement of the car? How far has it moved from here to here? So it's moved along. Well, now we'll be talking about angular things. So if you can see these formulas right here behind me, these formulas, you may look at them quickly and say, well, they look Greek to me, and that was a joke, because all of these mostly are Greek letters. The T is not. So if you look back in your notes from Chapter 2, we had something called the 4 formulas of acceleration. So we just didn't use that word. We called it the 4 formulas of acceleration. Now we're talking about the 4 formulas of angular acceleration. And all I've done here is I've replaced the linear pieces with the angular piece. So it used to say V final equals V initial plus A times T. That was for a linear quantity. Now we're saying the angular final speed equals the angular initial speed plus alpha, the angular acceleration, times time. Over here I'm saying the angular displacement equals the initial angular speed times time plus 1/2 the angular acceleration times time squared. And we have the other ones also. These are the exact same four formulas that we studied in Chapter 2, and now we're just writing them for angular pieces. Okay, so you want to make sure you've written those correctly. Here I have a problem that says we have a wheel with a radius of 40 centimeters, and it's rotating from rest, so the beginning velocity is 0, and it says it's going to end up getting to a speed of 900 RPMs, that's revolutions per minute, and it's going to do this in a time going from a speed of 0 to a speed of 900 revolutions per minute in a time of 20 seconds. The questions are, find the angular acceleration, and then find the tangential acceleration. The tangential acceleration, you should have read in the book, is basically the linear acceleration. So let's find both of those. So right here the radius is 0.4 meters. We have to be careful of that. We don't want to use the wrong units. Right here, this is an angular velocity, but it's in the wrong unit. So we would say that the angular initial velocity is 0 radians per second. We would say that the final angular velocity is 900 revolutions per minute. So we're going to have to convert that. In 1 revolution, we have 2 pi radians. And then in 1 minute, we have 60 seconds. So if you do that on your calculator, it's 94.25. So this is 94.25, and it's radians per second. Another given was the time. They told us the time here was 20 seconds, so the time is 20 seconds. Then we're looking for the angular acceleration, which is this letter here, alpha. So if I just plug it into a formula, I'd use this formula. Omega final equals omega initial plus alpha t. It's the same type of a formula what we did in Chapter 2. We talked about a final velocity equals an initial velocity plus an acceleration times a time. But these are all these Greek variables, so they're all the angular pieces. So the final angular velocity is this, 94.25 radians per second squared. Radians per second equals the initial velocity was this, 0 radians per second. And plus, the angular one is what we're looking for, angular acceleration, and the time was 20 seconds. So the 0 doesn't do anything here, just cancel it out. So we'll divide both sides by 20 seconds. And we'll come up with, on one side we'll have the angular acceleration, and on the other side we'll have 4.71. So that's meaning that the angular acceleration is the number 4.71 radians per second squared. So we've got the first piece here. And now the second piece is, what's the tangential acceleration? What is the basically the linear part of the acceleration? So if I can erase the top piece here for a moment and just show you. So the question they asked us is find the tangential acceleration. So what that means is, if we had a circle, okay, if we look at any point whatsoever on the circle, if we look at this point in the circle and somebody starts this thing up, the circle would be spinning this way. So the circle is this rotate, and it has a little point right here. So somebody, let's say it's a tire, and somebody has a little spot of paint on it. So the tire starts to spin, and if it's not spinning too fast, you can actually see the piece of paint, the little dot of paint, and it would be moving in a circular fashion. So we would say that the angle here is increasing by 4.71 radians per second each second. So it's going through an angular speed, and that angular speed is changing and increasing every second. But what about the linear pieces here? If this piece is going, so let me take this out. If this piece, the angular speed is here, so we know that the angular piece, we know it had a we know it had a 0 angular speed at the beginning. It had a 94.25 angular speed at the end, and we want to figure out the linear acceleration based on the angular. So we just figured out the angular acceleration. So alpha here would be 4.71 radians per second squared. Now, at this particular moment, this object would be facing this way. So there would be a linear acceleration based on the angular acceleration, and they use the word here tangential because we're talking about the tangent line. So the tangent line is a straight line that touches a circle at one point. So this would be a tangent line. So when they talk about a tangential velocity or a tangential acceleration, it's the linear component of the angular piece. So a few minutes ago on the screen, I had written this. I said the acceleration linear is equal to r times the acceleration angular. So sometimes the books will use a little this, subscript t, and that subscript t means tangential. So we know that the radius was 0.4 meters, and we know that the angular acceleration was 4.71 radians per second squared. So if I just plug that into my calculator, it comes out to be 1.885. So this is 1.885, and it's meters per second squared. So whenever you have anything spinning, there's a linear relationship to the angular relationship. So whenever you have anything spinning, there's a linear relationship to the angular. Whenever you have anything spinning, there is a relationship between the linear quantity and the angular quantity. Okay, that's how to do this problem. Here we have a sample problem dealing with a car driving down the road. We are told that the car starts from rest, and we are told that the car is going to reach a speed of 20 meters per second in a time of 10 seconds. And we are asked for two things. One, we are asked for the angular acceleration, alpha. And the second thing is we are asked for the number of revolutions that the tire will make. Okay, so that's the question. So there's a number of different ways you can do this. You can work with the linear pieces, and you can work with the linear pieces, and you can then find the answer in a linear fashion, and then convert the linear fashion into the angular quantities. Or we could take our linear pieces at the beginning, turn them right away into angular quantities, and then find the answers that way. So it's 50-50. So I will do this. I will work with the angular pieces. So I'm going to convert. So I'm going to say my initial, so it should be omega. My initial angular speed is 0 radians per second. I'll say my final angular speed is, well, it's unknown. You see, they told me my final linear speed was 20 meters per second. So I have to convert that. So over to the side here, I will say, if I had 20 meters per second, there's a formula that says the linear speed, it's actually tangential again, equals r times the angular speed. So 20 meters per second is the linear speed, 0.2 is the radius, and we have to solve for the angular speed. So if I divide both sides by 0.2, and this is meters, a radius has a unit of meters. If I do that, it'll come out to be 100 in its radians per second, and that equals omega. And we are talking about the final, so this would be omega final. So right here, I've just discovered omega final. It's 100 radians per second. And the other thing they gave me was 10 seconds. So the time here is equal to 10 seconds. So they want to know what is my angular acceleration. So to get that, I will use a formula. I will use omega final equals omega initial plus alpha times t. So this is my final angular velocity, my initial angular velocity. This is my angular acceleration, and this is my t. So I can plug those numbers in. This was 100 radians per second. This is 0. This is unknown. And the t came out to be 10 seconds. So if I divide both sides by 10 seconds, what comes out here is that's gone. And 100 divided by 10 is the number 10. Radians per second divided by seconds is 10 radians per second squared. And that equals alpha. Okay, so that's how to do that particular piece. We have alpha. So what's happening now for part B is they want you to know they want you to find the number of revolutions the tire will make in that 10 seconds. They're being tricky because they're not asking us to find the angular displacement. They're asking us to find an angle in specific units of revolutions. So what I'll do is I have these four things. I can use any formula at all that I want. I'll use this formula. So this is one of the formulas. My displacement, angular displacement, is equal to 1/2 my initial angular velocity plus my final angular velocity times the time. So when I plug that in, 1/2 times 100 is 50, and 50 times 10 is 500. So my displacement comes out to be 500, and it's radians. Okay. Now, that's an answer, but it's not the answer, because they wanted to know how many revolutions are going to be involved with this. So I would have to now go and convert out of radians. So What I know is in 2 pi radians, there is 1 revolution. So you see, this is basically over 1. So 500 radians, and I'll cancel out the unit of radians when I multiply this. So the radians on the top will cancel with the radians on the bottom, and the number will come out to be 79.57. So this comes out to be 79.6 revolutions. So this particular tire, they told us the tire had a radius of 0.2 meters, and with that number there, we were able to go and change a linear velocity into an angular velocity, and then we were able to go and figure out how many revolutions this tire will do if it's traveling for 10 seconds at either this linear speed, or in the same time, this is the same thing for the tire, it's the angular speed. So we were able to just push this all together, and we came up with almost 80 revolutions that tire will go through. And that's how to do this particular problem.